Transitioning from dihydroxylation into oxidative cleavage through first examining the oxidative cleavage of Syn-1 2-Diols with periodic acid, we were able to follow up the product of treating the alkene with osmium tetroxide, which was the Syn-1 2-Diol, and then treat it with periodic acid, which results in the oxidative cleavage. This unique mechanism occurs because the Syn-1 2-Diol can form a specific intermediate with periodic acid, which then breaks down, giving us our oxidized product, carbonyl, which is either a aldehyde or a ketone, depending on the substitution of the alcohol. The other mechanism of dihydroxylation is forming an anti-1 2-Diol through first forming an epoxide and then treating it through acidic conditions. These diols do not interact with periodic acid because they cannot form important intermediate with the iodine. With that in mind, looking at this review question, if we treat this alkene to the anti-dihydroxylation pathway of forming the epoxide and then acidic condition, why does it then form a cleaved product with periodic acid? The key here is that we have an acyclic example. In the past, we were looking at cyclic examples that lack rotational freedom along that axis. So in this case, we may form the anti-1 2-Diol, but because we have rotational freedom, we can then rotate the molecule to the syn configuration that can then interact with periodic acid. But keep in mind whether or not you're working with an acyclic or cyclic example while working through these reactions.